What is Bayesian modeling? Let's see. Handling uncertainty is important in many real-world phenomena. For instance, suppose you're building a model for a self-driving car that is detecting vehicles on the road. It's possible for the model to get confused with a long trailer on the side with the open sky, and this could lead to an accident. Instead, if the model could say that it is not sure about its prediction or outcome, then we could switch to a manual intervention and avoid an accident. So it's very important for models to know when they do not know. So Bayesian modeling comes to the rescue here. So it's a tool that can help probabilistic models figure out when they do not know. So let's see an example. Suppose you have a biased coin where, let's say, P is the probability of heads. You observe 3 tosses in which you have 2 heads and 1 tails. What is the probability of heads? So logic or intuition, common sense says that probability of heads is the number of heads you saw divided by total number of tosses, which is 2 by 3. And this is also called the maximum likelihood estimate. So in case we want to recap MLE estimate, maximum likelihood estimate, the MLE estimate maximizes the likelihood of the observed data. So if we represent the coin tosses by x1 through xn, then the likelihood is nothing but p power n, which is n is the number of heads here, small n, into 1 minus p to the power number of tails, capital N minus small n. So this is just the Bernoulli distribution for a bunch of coin tosses. So now the maximum likelihood estimate involves finding the value of p that maximizes this expression, and it turns out to be small n by capital N, which is the number of heads divided by total number of tosses. Okay, so what now if we have 2 tosses and observe 2 heads? Now the probability of heads is 2 by 2, which is 1, which means the probability of tails is actually 0. But is this a meaningful answer? Probably not, because we might be predicting from too little data here. We actually might be overfitting. Okay, let's say we have 6 tosses and 4 heads. What is the probability of heads? Once again, it's 4 by 6, which is 2 by 3. Now, if we have 600 tosses and 400 heads, once again, the probability of heads is 400 by 600, which is 2 by 3. Now, are all these 2 by 3s the same? Probably not. Because in the first case, we just saw 3 tosses, and we can't be very sure that we are making the right, estimating the right value of p. But when we see 600 tosses, we probably are more sure about p being 2 by 3. Now, how do we actually quantify this sureness apart from just, predicting the 2 by 3? And that's where Bayesian modeling comes in. In Bayesian modeling, instead of learning a 2 by 3, we actually learn a probability distribution over the value of p. So for instance, we can start with a prior belief or a prior distribution for p. So this is our assumption of what a distribution for p looks like. And this could even be, okay, I give equal weightage to all values between 0 and 1 for p. That could be possible. Or I could give more weightage near 0.5 if I believe that a normal coin is more likely to be a fair coin. Right? So we start with a prior distribution for p. We look at the actual data, and then we find a posterior distribution which modifies this prior based on the data. Now, what is the advantage of the posterior distribution? It's a distribution for p and not just a value. So the variance of the distribution will tell us how confident we are about our prediction for p. So let's work this out for the coin toss from a high level without going too much into the mathematical details. So first I need to come up with a prior distribution for p, and a nice distribution I can use for this is the beta distribution. So let's not worry too much about the mathematical expression for the beta distribution, but essentially what the beta distribution says is it has 2 parameters a and b, and a is the bets or the weightage that I'm giving to heads, and b is the amount of bets I'm putting on tails, or the weightage that I give to tails. So if I think it's a fair coin, I can just have 1 and 1 for a and b, or I can have 2 and 2 if I'm more confident that it's a fair coin, right, and that the probability is closer to 0.5. So I can put my bets on heads and tails with this a and b parameter, and this is my prior distribution. Now, once I observe some data, I want to compute the posterior distribution. How do I do this? So I multiply the prior with the likelihood. The likelihood was what we computed earlier. So the likelihood is just p power n 1 minus p power n minus n for n coin tosses. So we use the likelihood. When we multiply it with the prior, we get some expression like this, which is again another beta distribution. But the difference is this time, our bets for A are augmented by the number of heads we saw, and our bets for tails is augmented by the number of tails we saw, which is capital N minus small n. So it's just a beta distribution with the new parameters where the bets for heads and tails are augmented with the data. Now, what is the Bayesian estimate? Now, if I ask you, give me one value for P, I'll probably take the mean of this posterior distribution, which is nothing but the first parameter divided by the sum of the two parameters, which is small n plus a divided by capital N plus a plus b, which is the number of heads that I already saw plus the original bets I had for heads divided by total number of tosses plus the number of bets for heads and tails combined, right? So this actually makes a lot of sense, and this is also called smoothing sometimes, where instead of just taking small n by capital N, we are adding some value to the numerator and the denominator, and this also effectively helps us not come up with like zero. For instance, if we see two heads and two tosses, we will not predict p equals 1 here, right? And probability of tails won't be 0 because we are adding these small quantities in the numerator and denominator. Let's look at it visually. So let's say I give an initial prior distribution which says that there is equal odds probability for all values of p. So I do not know, what value is more likely for p initially. Now, when I see two trials and two heads, we see that most of the density is concentrated near 1, which is 2 by 2, but other areas, other values of p also have a non-zero probability. A smaller one though, but yes, non-zero probabilities. Now, if you see 10 trials and 8 heads, I have this PDF which is peaking at 8 by 10, right? And if I have 20 trials, it is peaking at 11 by 20, which is number of heads by 11 is probably the number of heads here. And if I see 50 trials, this is what I see. If I see 500 trials with 232 heads, it's peaking somewhere around 232 by 500, around that place. Now, what we see here though is that when we have 500 trials, this PDF is very peaked, or the variance is very low, which means we are more confident of this when we actually look at this PDF, as opposed to when we had 10 trials where the variance is much higher, right? So this is an example of how Bayesian modeling can help here in terms of for the coin toss example. So where do we actually use Bayesian models practically? Let's look at some common algorithms we use and how Bayesian will help there. So an example is logistic regression. So if you recall, logistic regression helps us model the probability of success as a sigmoid of W transpose X, where X is the features and W is some weights given to them, right? So what I can do is I can put a prior on these weights W. How does this help? So logistic regression already gives us a probability for success, probability of Y equals 1. So it's already telling us, not just true or false, but a probability between 0 and 1. But how confident are we about this probability itself? So let's say that, for a particular test instance, it gives probability of success is 0.8. How confident are we about 0.8? Right? So a Bayesian logistic regression model will help us give a notion of that confidence. Bayesian deep learning. So in a deep learning model, we can put priors over the weights in a neural network. That's Bayesian deep learning, one form of Bayesian deep learning. Bayesian linear regression. Suppose we are modeling a line y equals mx plus b using linear regression. Can we put a prior on the m and b, for instance, right? Or whatever weights w transpose x, can we put prior on those weights w, right? So these are some ways in which we can augment some of the commonly used machine learning models we know to be able to handle uncertainty better in these models. To recap, we saw how Bayesian model helps by not coming up with a point estimate like 2 by 3 that maximum likelihood estimate did, but instead finding a distribution over the unknown parameter we want to learn. By seeing the variance of the distribution, we can say whether we are confident about our prediction or not. The mean of the distribution could give us a parameter estimate, right? So we start with the prior or some initial distribution for the parameter to begin with. We look at the actual data and modify it to come up with a posterior distribution. And we saw some real life, very common machine learning models that could be augmented with the Bayesian technique to handle uncertainty. Hope you liked this on Bayesian modeling. Thank you.